Good morning, ladies and gentlemen. My name is Yachin Cohen. I'm a professor in the Faculty of Chemical Engineering, as well as the Dean of the Undergraduate Studies. By the way, there's no School of Undergraduate Studies in the Technion. I have a great pleasure of being your Master of Ceremonies today. We are celebrating today, in fact, two occasions. The inauguration of the newest award donated by Mr. Norman Seiden. This is the Norman Seiden Award for Academic Excellence, as well as the distribution of the annual Barbara Norma Seiden Prize for multidisciplinary undergraduate student projects in optoelectronics, microelectronics, and nanosciences, which is being given to students. The Norman Seiden Award for Academic Excellence was established by the children of Mr. Norman Seiden in honor of their father's 90th birthday. Congratulations. Two of the donors are here with us today. There are Stephen and Sharon and Mark and Diane Seiden. Okay, thank you. Ms. Pearl Seiden was unable to attend today's ceremony. Awards for academic excellence enable the Technion to retain the best of its research faculty. Such winners make huge contributions to the Technion, Israel, and to people worldwide. The prizes provide not just a financial reward, but also public recognition. We are grateful to Stephen and Sharon, Mark and Diane, and Pearl for honoring their father in this way. The prize for students was established in 2005 in honor of Norman Seiden's 80th birthday. This is a unique award given to outstanding Technion students who choose to embark on a path of multidisciplinary research already in their undergraduate years. As such, the idea behind the Seiden Family Prize captures the very spirit of the Technion as Israel's only technological university in which pure science not only resides with, but is essentially woven into applied research projects. As we enter the second decade of the 21st century, multidisciplinary research, which has been the core of Technion's very existence throughout its almost a century-long history, is recognized as holding the key to the most pressing challenges facing the humanity today. The talented young people honored by the Seiden Family Prize represent the enormous potential of our students, which, coupled with passion, determination, and professionalism, places them at the forefront of this worldwide effort and enables them to successfully tackle real-life problems at the earliest stages of their academic career. We express appreciation to the Seiden family for helping our promising scholars, Israel's future leaders, realize their dreams to theirs and our benefit. Well, I would like to invite Professor Moshe Sidi, Senior Vice President, to the podium to greet the guests. Please.
Dear members of the Seiden family, Norman, Stephen and Sharon, Mark and Diane, dear colleagues, distinguished guests, ladies and gentlemen, once again, as Yachin said, we have gathered here in what has become a wonderful yearly tradition, awarding the annual Norman and Barbara Seiden Family Prize for multidisciplinary undergraduate student projects in optoelectronics, microelectronics, and nanosciences. And also, for the first time, we are dedicating today the Norman Seiden Award for Academic Excellence. The Seiden family members with us today present generations of Technion commitment. I'm not sure how many people in this room actually know that upon Norman's graduation from Purdue University, his parents honored him with a commemorative plaque which still hangs in the Churchill Auditorium as a founder of the Technion. This wonderful and generous commitment, yes, this wonderful and generous commitment continued with a lifelong generosity and dedication of Norman and his beloved wife Barbara of blessed memory. This commitment continues with the active support and leadership demonstrated by you, Stephen and Sharon, Mark and Diane. In fact, the first part of our program, the dedication ceremony of the new Norman Seiden Award for Academic Excellence, is a testimony of the continuing dedication which in the great tradition of the Seiden family is not only very generous, but also very well suited to the contemporary needs of the Technion. You will very soon hear from the first recipient of the new award, Professor Jacob Rubinstein, about his work and the significance of the award. My dear friends, as we look into the future and the challenges ahead of us, here at the Technion and the State of Israel at large, it is very clear that the true challenges are not necessarily the challenges we are familiar with and try to prepare for, but those we have no idea about yet. Those challenges usually bring with them not only concerns, but also great opportunities. Such has always been the case when it comes to science and academic research. The Technion has done quite well in exploiting many of those opportunities. Others have come and gone without us being able to exploit their potential to its fullest. When I look at those cases, successful and unsuccessful alike, it is very clear to me that what makes a huge difference between success and failure is the support from people like the Seidens, people who combine between their incredible generosity and dedication, as well as the ability to identify the true needs the future may bring. We cannot thank you enough for what you have done and for what you are about to do. Thank you from the bottom of our hearts. I would like to conclude by congratulating the three student groups that are soon get the Seiden Family Prize, and we are all looking forward to hear about your achievements. Thank you.
Thank you, Professor Sidi. I would like to invite to join me at the podium Professor Hagit Atiyah, the new Vice President for Academic Affairs. Professor Atiyah, please. The first Norman Seiden Award for Academic Excellence is given to Professor Jacob Rubinstein from the Faculty of Mathematics. To present the award, I'm honored to invite Mr. Norman Seiden to the podium. Please come up. I invite Professor Jacob Rubinstein. Please come up. You can present the award. You can open it. Congratulations, Jacob. Thank you, Mr. Seiden and Professor Atiyah. Professor Rubinstein will now respond.
Okay, thank you very much for the award. Thank you, Yachin. I was asked to talk about my work. Now, this is a very dangerous thing to ask a mathematician to describe his work because he might actually do it. So, fortunately, I am doing applied mathematics. So, talking about the applications of my work. And in recent years, all the applications of my work is applying mathematics into medicine. For example, a joint project just finished with the urology department at Bnei Zion Hospital in Haifa about advanced mathematical tools that are going to be used now in the clinic in urological oncology. Another specific product is my spectacles. These are multifocal spectacles. They were designed based on a code an algorithm developed here at the Technion and transferred by the Technion to an Israeli company. And by consumer report, independent consumer report studies, these lenses are the best in the world. Made by this company in Kibbutz Shamir. Talking about spectacles, future and present project are special spectacles still not on the market, where each lens is replaced by two lenses. When you shift them respect to each other, the optical power changes. And we designed these lenses to cure functional blindness in developing countries. In developing countries now, there are nearly 200 million people simply don't have glasses, don't have prescription, no optometry there. The idea is to give them adjustable spectacles, which is screw here. They can turn the screw, change the optical power until they see well, then they can use this spectacle. In addition to working with Nathan Hospital, we have other joint project now with Haifa Hospital. Yesterday I spent the entire afternoon, 3 or 4 hours, at Rambam Hospital, at the ophthalmology department. We are now, together with them, are developing several projects, hoping to improve understanding vision, curing visual defects, and also curing pathologies in ophthalmology. And let me announce that I plan to use this award for one thing, to hire research assistant to do this joint collaboration with the ophthalmology department at Rambam. And thank you very much.
That's wonderful. Thank you, Professor Rubenstein. Now, I would like to invite Professor Gadi Eisenstein to the podium to present the Seiden Prize for students.
First of all, Kobe, congratulations again. I knew you were a great mathematician. I didn't know you had interest in practical things, so bravo. I want some of these glasses also to show off when I talk about Technion to people. Anyways, so in 2005, well, just one step back, it is very hard to look for something that the Seiden family has not contributed toward for and helped developing in Technion, in research and teaching and this and that and the other. And in 2005, when Norman was either 80 or about to become 80 years old, this issue came up. What to do to honor him, of course, in relationship to Technion. And then came this idea that the one area that was, I don't want to say neglected, but wasn't so much highlighted by the key donors of Technion is the support of what is really one of the prides of our university, and this is the extremely high level of undergraduate project all across the campus. Many of these projects, I have been here for many years, and so I can testify from firsthand in my department, but also in others, could easily qualify as all, or at least most, of a master's project in many respectable universities, which we always like to compare ourselves with. So came up this idea to pick this group of people, to point at this group of people, the students who do their mandatory undergraduate projects, and to concentrate on those students who do their undergraduate research in the areas which we know are close to the heart of Norman Seiden. So this is optoelectronics, which he's the father of in our university and in this country, actually. Nanosciences, which is the next generation, and micro and nanoelectronics, which has been a big traditional in Technion for many, many years. And so this has come to be that every year we have a call and people apply, and then we make a little committee and we choose projects in those areas. And this has been now for 10 or 11 years, extremely successful. Many of these students are now our graduate students. Some of them are already postdocs and may soon become possibly the future academic staff in our university or other universities in Israel. And I'm very happy to carry this torch and every year be responsible for arranging this. And I should say this year, perhaps because we are a little bit shifted in time, because this year, usually this is awarded at the board meeting in June, but this year somehow it was delayed by 6 months. So possibly because there was a little bit longer time, the number of applications and the quality of the application was really unprecedented, even by the high standards, which I have already said before that the projects usually are. So much so that it was difficult to choose, but at the end, what can you do? You have to choose. So we chose, and you will hear in a few minutes the winners. But we will, for the first time, at least I have decided that all the applications that did not win will automatically be applicants for the one coming up next June, because simply, first of all, it's very little time till next June, so that's easy from the organizational point of view. The students are still going to be here, and also the quality was such that they deserve a second chance, and maybe one of them will be on the podium in the board meeting in June. So I hope this tradition will continue for many years. It's very important for the students. I think it's very important for the people who guide this project. These students are guided usually by a graduate student, sometimes by a faculty member, and it became a very important part of our system and will continue for many years, and we will now celebrate 3 of them. We always have a little bit of a problem that the students, they're very talented. Of course, they're not so experienced, so sometimes they present 5 or 6 minute talks, which are a little bit too technical. So I hope this time it will be for the laymen. We are also laymen, not only the guests, when it comes to the stuff. Because the projects are of such high level that if you are from another field, even if you're a scientist, sometimes you cannot follow. So I hope you prepared well, but we will enjoy anyways. Thank you very much.
I please call Norman Seiden to come up to the podium and join us for the awards. I will invite the recipients to the podium individually by calling their names. Please approach the podium to receive your prize for Mr. Seiden. I call upon Eyal Rosenthal and Sergei Gershnikov from the recently called Andrew and Erna Viterbi Faculty of Electrical Engineering in the area of nanoelectronics. They are receiving the prize for their work, a fully analog memristor-based neural network with online gradient training. If you hold them open for the photography. Thank you. Congratulations. I call upon Raja Margier and Eviatar Sabag from the Andrew and Erna Viterbi Faculty of Electrical Engineering in the area of optoelectronics. Their work is light amplification in semiconductor superconductor structures. So, Raja? Congratulations. I call upon Ran Eshel and Yaron Edri from the Faculty of Mechanical Engineering in the area of nanoscience. Their work is asymmetry-induced electric current rectification in perm-selective systems. Congratulations. Congratulations to all prize recipients. I would now like to ask Mr. Seiden to take a seat, and we will now hear the students presenting their work. I guess you can take your seat also. Our first group of presenters will be Eyal and Sergei.
Hello everyone, my name is Eyal. I'm here to present our project together with my partner Sergei, with our advisor Shachar Kvatinsky. It's called implementation of a multi-layer neural network with memristors. I'm sure this means nothing to everyone, and we will try our best to explain it. Let's start with machine learning. What is machine learning? It's basically a form of computer algorithm that allows us to teach a system how to perform a certain task, and the system updates itself accordingly. Machine learning is used almost everywhere today. Many of the major companies use it, like Google and Facebook, for various devices and the search engines, or things like the Google's automated car, and we see it on a daily basis on our smartphones for many of the apps we use. A neural network is a form of machine learning. It basically emulates the function of our brain and how our brain processes information. If we look closely inside our brain, we have nerve cells called neurons. Each pair of neurons is connected by a link called a synapse. Information is passed from one neuron layer to the next through the synapses, and this is how our brain actually processes information. When we want to artificially create a neural network, we use the same principles as our brain. We have a layer of neurons which act as inputs, a layer of neurons which act as outputs, and a synaptic grid which connects between them. The thickness of the arrows that we see here actually represent the weight of the synapse. It tells us how much of the information from one neuron is passing along to the next. The stronger the weight, the stronger the link is between two neurons, and the more relevant the data is for whatever it is we want to do. So basically, we have two phases: the phase where we train the system, and the synapses update themselves and change their own weights. And later, when we finish training, synapses retain their weights, and the system can perform its task. There are many ways to train a system. One of the methods, and the one we use in our project, is called backpropagation. To put it simply, we give an example for the system. We tell it what is the outcome that we want for this example, and the system updates itself accordingly. This type of design is called a single-layer neural network. We have one layer of inputs, one layer of outputs, and one synaptic grid connecting between them. If we chain together a lot of these networks, we'll receive a multi-layer neural network. What is it good for? You can see in this example. This is a system that receives an image as input, and at the end it tells us, is this an image of a horse? Yes or no? Identify what is in the picture. We can see that information, when it passes through the synapses to more neuron layers, the information is broken down into smaller segments, each time getting into more details, until eventually we can recognize certain parts. Okay, this is the leg, this is the head, and so on. At the end, this information is aggregated, and we receive the answer. The more layers we have in a network, the more we can go into details, and the more we can receive accuracy at the end.
There are two ways that we can implement a neural network. We can use software to implement it, and we can use dedicated hardware to implement the network. Both implementations have advantages and disadvantages to create them. Since the algorithm is written in mathematical equations, it's naturally easier to implement it in software. Also, as the learning task gets more and more complex, you need a larger network to implement the algorithm. More synapses, more neurons. Even if we run the software implementation on numerous CPUs and GPUs, it still takes much time to implement the algorithm, and it takes slower and slower time as the networks get larger and larger. On the other hand, a hardware implementation is much faster. In fact, it doesn't get any slower as the network size gets larger. To implement a dedicated hardware implementation, there are many components that are designed to do a specific task. The smaller the components are, the larger the network that we can create in hardware. One of the components in the network is the synapse. The synapse is the basic weight unit that shows how the neurons interact with each other. Using conventional methods is very difficult to create a synapse because it requires many, many components. In order to overcome this issue, we have decided to use a new technology, a device called the memristor. The memristor is a relatively new device. It was first introduced in 1971, but only in the last few years, many major companies have started using this device. HP, in the last few years, announced it created the memristor. Intel, a few months ago, announced that it created a memory component called the 3DX point. It's fast and small. Basically, the memristor is a resistance with varying resistance. It can change its resistance in the following way. If this is the symbol of the memristor in analog circuits, if we have current flowing from the left to the right, its resistance is increasing. And if current is flowing on the other way, the resistance will decrease. Also, if we switch the power of our system back off, then the next time we turn it on, the resistance will be kept and it will not change. This functionality of the memristor makes it a very effective memory device. We have used this device in the synapse. This is the design of the synapse that was suggested by our advisor, Shachar Kvatinsky, in a paper he wrote. The synapse consists of 2 transistors and a memristor. A transistor is a device that acts like a switch. It can have current flowing through it, and it can have the current turned off. In this way, this functionality of the synapse can have current flowing in both directions, from the left to the right and the other way around. This allows us to change the resistance of the memristor any way that we want. The resistance of the memristor is basically the weight of the synapse, and it modifies the interaction between the neurons in the network. This allows the network to learn and adapt. The simulations that run in the article, in the paper that our advisor wrote, were using ideal components around the synapses. In our project, we have used a fully analog multi-layer neural network with practical devices. Some of our circuits that we have created are shown here. If we combine all the circuits together, we will create a multi-layer neural network that is capable of learning. We run our simulations on a relatively small neural networks, and the results and the conclusions are as follows. The network, if we compare our analog simulations with the software implementation, we had very good accuracy. Like I said before, our network was relatively small, and we achieved 1,000 times faster than software. So you can imagine that if the networks get bigger and bigger, we will achieve more and more training time better. Also, if we compare our hardware implementation to previous designs, we're 20 times at least better in terms of space usage.
To conclude, the main problem with implementing a hardware neural network was the synapse. It was usually very complex, very big device. And by using this simple device called the memristor, we can see we get a very simple design for a synapse and a very effective design as well. Our project confirmed that the design is very practical and very effective. That's all. Thank you.
And I now call Raja and Evyatar. Please come up and present your work.
So, my name is Raja, and this is Evyatar, and our project is entitled Two-Photon Amplification in Semiconductor Superconductor Structures. So, before we start, we will give a very short background about the related concepts in this project. So, we start from superconductivity. Superconductivity is tightly related to the concept of Cooper pairs, where Cooper pair is simply a pair of electrons that are in a bounded state. Electrons on their own are fermions, and therefore, by the Pauli exclusion principle, they can't occupy the same quantum state, and therefore they can't form a condensation. When Cooper pairs, when electrons combine and form Cooper pairs, they become bosons, and then they can form what we call a quantum condensation. And basically, superconductivity is the outcome of this condensation of Cooper pairs. This was first explained by Bardeen, Cooper, and Schrieffer in their BCS theory, for which they won the Nobel Prize. Okay. The second important ingredient in our project is photonic emission processes, where we distinguish between one-photon emission processes and two-photon emission processes. So one-photon emission processes could happen in two different scenarios. We have the stimulated OPE, where an electron emits a photon spontaneously. And the other case is the stimulated case, where we have a photon stimulating the transition of the electron, and by that, the emission of another photon. This stimulated OPE is what we call one-photon gain, OPG. Okay. The other and more relevant emission processes are the two-photon emission processes, and they could happen in three different scenarios. We have the spontaneous TPE, where an electron, instead of emitting a single photon, it emits two photons. We have the singly stimulated TPE, where instead of the process spontaneously happening, a single photon stimulates the transition. And finally, we have a fully stimulated transition, where two photons simultaneously stimulate the transition, and by that, the emission of another pair. And this last process is what we call two-photon gain. Okay. So the general idea behind our project, what we have shown is that by using the framework of quantum field theory, we demonstrated actually theoretically that that if we can combine superconductivity with two-photon emission processes and semiconductors that are present everywhere in modern-day technologies, and ultra-fast optics, this results in enhanced two-photon gain. Okay, and this is interesting because this two-photon gain has many remarkable properties that could be related to many fields. For example, one could think of future efficient quantum entangled two-photon sources. There have been papers that relate this combination of superconductivity and TPE to quantum entanglement of photons. Also, it could result in systems that work on lower seed densities. It has been demonstrated that, for example, this two-photon gain could result also in ultra-fast pulse compression and many more other interesting properties.
Okay, so here we have our proposed device, which is in a form of a ridge waveguide. Here we have a regular PN junction, such as in any diodes, but with the small difference that here we have our superconductor in yellow above the end part of the PN junction. This superconductor actually reflects its injects its Cooper pairs inside the end part of the junction, which gives us the part that actually gives the two-photon gain. Here we can see our photons where they propagate in this direction and get amplified. And now we'll see a few graphs that shows the results of our project. First, we'll look at this graph where we have dependence on temperature and normalized photon energy, where we see here by the colors where we get the most powerful gain. We can see here at the bottom we have at the superconducting band gap, which is 1 here, which means delta, and we get the most powerful gain. And as we can see, as expected, when the superconductor goes to higher and higher temperatures, his qualities decline, and we get it that this peak declines also. Next, we will look at the relative two-photon gain divided by the one-photon gain to see actually how powerful it is. So here we can see in this graph, we can actually see that that around 10 to the 7 number of photons per pulse, we actually get that the 2 photon gain actually equalized with the 1 photon gain. Okay, and this is one of our main results. This is actually several orders of magnitude lower than the case without superconductivity. So actually what we get here, we put less photons inside, but we get just as much amplification.
2 photon amplification.
Yeah, 2 photon amplification related to other similar devices. So we conclude, we have here our proposed device with superconductivity. We actually got the 10 to the 7 number of photons that is several orders of magnitude higher than any other 2 photon amplification.
Lower, you mean?
Lower than any other 2 photon amplification. And
yeah, I'll add just one more sentence, is that basically by the introduction of superconductivity into well-known semiconductor structures, one could get very interesting phenomena that are, for example, quantum, that we're not, and this is a whole new field that one could explore. That's all.
Last couple in our presentation, this is our Ran and Yaron. Please come up and present your work.
Greetings all. Both Yaron and I are deeply honored for being awarded with this prize and want to thank everyone's involved. We are proud to present our research, which was part of an undergraduate project in the Micro and Nanofluidic Laboratory, headed by Professor Gilad Yossifun. Our research advisor is Yoav Green. Yoav defended his thesis successfully 3 weeks ago and is currently in the US searching for a position. And he couldn't join us today. Our work is to characterize a nanochannel system. Sorry. And it was divided into 2 different efforts, as you will see shortly. The guiding idea to describing such a system is to consider it as an electrical circuit, compromised from day-to-day components such as resistors and diodes. But let's start off by describing the system. Okay, so our system is compromised from 2 microchambers connected by a single nanochannel. The microchamber height is around 50 microns, which is the same as the diameter of your hair. And the nanochannel, which is 100 times smaller, is around 200 nanometers. We then insert electrodes to the microchambers and apply voltage. And then we want to consider the system as an electrical circuit. And perhaps I should mention, but the current isn't compromised from electrons, but rather from charged ions. And due to its smallness, the nanochannel, which is here in the middle, exhibit peculiar behavior.
So when you put an electrolyte, which is a fluid with ionic charges within it, near a charged surface, some of the ions will be attracted and some will be repelled. In our case, the surface is negatively charged. Therefore, the positively charged ions will be attracted and the negative will be repelled. If we were to plot the concentration as a function of the distance from the wall, we would see that near the wall here forms a layer of positively charged ions. The thickness of this layer scales as 1 over the square root of the concentration, meaning that for lower concentration, the length is bigger. The typical sizes of this layer is 1 to 100 nanometers. An interesting question arises when we have 2 surfaces, top and bottom. What happens when the spacing between those 2 surfaces is smaller than 200 nanometers? Well, as we already saw, the negative ions will repel from this volume, and we will remain with with a region where only positively charged ions can reside within.
It was shown in an earlier work that the nanochannel exhibit a peculiar behavior. In very high concentration, the resistance exhibit a linear reaction to the concentration. And in a very low concentration, it saturated to a constant level. It was assumed that due to its smallness, the nanochannel is the dominant resistance in the system, like the system that we showed you before. And all other components contribute a negligible resistance to the system. This assumption was remained unchallenged for a decade until our advisor, Yoav, started to research this assumption. And Yoav showed in his couple of works that the microchamber resistance isn't negligible, especially when we go to smaller concentration. We saw that the microchamber have the dominant resistance in the system. And my work was to prove this theory by experimenting it. So we fabricated a number of channels where we kept the geometry of the microchamber constant, and we varied only the width of the nanochannel. And by that way, we could see the interplay between the nano and the micro and nano channels resistance. We saw for the narrowest channel that we didn't saw any significant change, and still the nanochannel had the dominant resistance in the system. But for wider channel, we saw that the microchamber could contribute to the resistance of the system, and we measured the expected result. And this work was submitted to Nature Nanotechnology last week.
In my project, which was published in the Physics Review letter, we considered a four-layer system of general geometry of two microchannels and two nanochannel regions. We have both positively and negatively charged regions adjacent to each other. Today we will focus on a case where the height of the nanochannel is the same for all the regions. We derived the response for the current voltage behavior, and our analysis showed that the response is similar to a bipolar diode used in solid-state physics, meaning that in one part we have very high current, and on the other side we have very low current due to the diode effect. We also showed that the microchannels affect the total resistance of the system. We show here that the result of the current is changed with and without the microchannel.
Okay. So, for conclusion, the system resistance is dependent on the geometry of the system and also the concentration and
the current selective configuration.
Thank you for listening.
Thank you very much. Now the lights, thank you. Well, I now wish to call Mr. Norman Seiden to the podium to say a few words, if you choose.
As it was mentioned earlier, we've been doing this for 10 years, and part of the genesis was that my brother, sister-in-law, my wife and myself and my sister wanted to honor my father for his 80th birthday, but it was also a special anniversary for my parents. And in thinking about it, as was mentioned, it seemed like all the graduate students got all of the credit. And in my understanding, to build a strong university, to build any strong organization, you need to have a strong base. And the strong base of Technion has always been the undergraduates. So we saw there was an unmet need there, and that's why we chose this these prizes, because it wasn't just one, it's obviously three, and in areas that have been very near and dear to my father and our family. And I can only tell you, sitting here, well, I didn't understand the first year. Each year, while the presentations have become more understandable and better, I probably understand less because the quality of the presentations continues to increase. So, as a family, we take a lot of pleasure trying to understand the presentations, a lot of pleasure seeing young future scientists really show what they can do and what they've learned at Technion. So we're very excited and always look forward to, I especially look forward to this award every year. And I thank you, and I wish you continued luck as you continue to investigate, explore, and make the world better for all of us. Thank you.
Thank you very much. I congratulate again the award winners, and I want to thank again Mr. Norman Seiden and the entire Seiden family for the vision and support of multidisciplinary research on the undergraduate and senior level at the Technion. And this concludes the ceremony, but before you all leave, I would like to ask you, the Norman Seiden family and the family and the award winners, to come here for a group picture. So thank you very much and have a good day.